So in this video we're going to be looking at the astronomical magnitude scale, or how astronomers measure the brightness of stars. We're also going to be relating this brightness to the intensity and coming up with a few formulae, showing how these formulae are derived as well, so that you get a thorough understanding of the background to this material. So we're going to start by looking at this picture. This picture is a picture of Orion. It's a constellation. It's observed easily in the northern hemisphere, particularly during the winter, when it's above the horizon during night time. And so on a dark night you can go out and find this very easy to spot pattern of stars. You've got 7 stars, 4 on the outside and 3 in the middle. And then of course you've got a little sword hanging down from the middle belt as well, and we'll talk about that a little bit. So in our constellation, the 4 outside stars are Betelgeuse, or some people call it Betelgeuse, and then this one over here is Bellatrix. You might recognise that name from Harry Potter. Then here we have a bright star called Rigel, and a little tiny one over here called Saph. Okay, so we're going to be having a quick look at how we might interpret the data from this photograph. And you might think that looking at the width of the star is an indication of how wide the star really is, or how large the star is in reality, but that's not true. In fact, the visible width of the star on the photograph is caused by the diffraction of light, the 0th order maxima, as the light enters our telescope and diffracts around the various apertures that it needs to follow as it works its way either towards the eyepiece and our eye, or alternatively towards the camera. So a brighter a star is, the greater the width of this 0th order diffraction fringe and the wider the star looks. So in the 18th and 19th century, astronomers would use the width of the stars as an indication of how bright they were, and they actually based the magnitude scale on that. So we can see that our star here, Rigel, is brighter than Saph over here. And we can see that because not only does it look brighter in the photograph, but it also has a greater width. Now, of course, these days, modern telescopes accumulate all of the light coming, all of the photons coming from that particular patch of sky, and use that as a measure of the brightness or the intensity of the light that we observe. So the next thing we need to do is have a look at how the magnitude scale works for some objects that we might know, and have a look at how we can turn that into a mathematical formulae. So what we can see here is 7 objects with the magnitude values for them on the astronomical magnitude scale for brightness. So the first thing we'll have a look at is our own star, one of the brightest things that we can see, and it has a magnitude of minus 26.7. And then we can move down to our moon. That's not as bright as our sun, but it's still a pretty bright object. I often have to put a filter to cut out some of the light when I look at the moon and telescope, otherwise it looks too bright and hurts my eye. Depends on what telescope I'm using, but if I'm using a big 8-inch Schmidt-Cassegrain telescope, then it can be pretty bright, and so I use a little filter to cut out the light. That's at minus 12.9 on the scale. And you'll notice that as the objects are getting dimmer, as they're getting less bright, the value of the magnitude is going up. So the scale that astronomers use for magnitude is backwards. Okay, smaller values are brighter, larger values are dimmer. Sirius is one of the brightest stars in our night sky, has a magnitude of minus 1.47, and Vega was actually used as the reference star originally on magnitude scale for a magnitude of 0, and its magnitude now is very close to 0 as a result of that. It's just a little bit over 0 on a modern magnitude scale. but it was originally used as the zero, if you like, the reference star for the scale to begin. M31 is the Andromeda Galaxy. It's a whole cluster of stars, a whole galaxy of stars, and it's just about visible with the naked eye on a really dark night. And it's got a magnitude of plus 3.44. Uranus is the dimmest planet that you can see with the naked eye, so you can just about see plus 6 magnitude objects. And then up at plus 31.5, this is the dimmest thing that can be seen with the Hubble Space Telescope. So there's no way you can see this with the naked eye. In fact, you have to point Hubble at that patch of sky in order to be able to see stars of this, or galaxies of this magnitude, for many hours in order to be able to accumulate enough light for Hubble to even see a plus 31.5. So as of a few years ago, that's kind of the state of the art, really, with the Hubble Space Telescope. Now, we have got more modern telescopes coming online. The James Webb Space Telescope hasn't been launched at the point at which this video has been made, so we're looking forward to even better telescopes in the future. So, how does the magnitude scale relate to intensity? Well, it's relatively simple. A difference of 1.5 magnitudes, so that would be the difference between Sirius and Vega. Vega is dimmer, Sirius is brighter, but the difference between them is about 1.5. So the difference of 1.5 is actually a intensity ratio of 4. That is to say that Sirius is 4 times more intense, brighter than Vega. To get this figure, we simply take 2.51 and raise it to the power of the difference between the magnitudes. And then that gives us how much brighter one object is than the other. Now you'll notice that we've subtracted them to get 1.5, and then we've made sure to interpret that difference correctly by saying that Sirius has the smaller value of magnitude, and therefore it is the brighter object. Okay, here's another example. So here we've got 6.03 and 3.44, and we're taking the difference between these two magnitudes. So it's the difference between these two objects here, M31 and Uranus, and that turns out to be a difference in magnitudes of 2.59, like that. So if we raise 2.51 to the power of 2.59, we get 10.84. So that means that M31 is 10.84 times brighter, more intense, that is, its intensity is 10.84 times that of Uranus. So a difference of magnitudes is a ratio of intensities.